Okay, cool. So let's get started. All right. Yeah, sorry for the very long delay there. I'll get this process down with the new recording setup, and we should be good for future times. Okay, cool. So today we're going to talk about. We're going to get into a few different topics. Okay, Zoom. Yes, thank you, Zoom. We're going to get into a few different topics. We're going to get into lists as well as loops. So a quick overview. I'll do this very quickly. Types, abstractions, um, control flow, and iteration. Types we've covered: int, float. These are our numbers. Bool, also technically a number type. String. We've talked about none. I think is that everything? Am I missing anything? I think that's everything we've talked about to this point. And then today we're going to talk about lists. Now lists are a little bit different. They have, I kind of think about them as categorically different because they are mutable. And I'll talk about what that means in a second. These are immutable. These are immutable types. So I always like to break things out into, my immutable types and my mutable types. There are some immutable types that we haven't talked about that we'll get into later. But lists are our are our first mutable type that we're going to talk about. So what a list does, let me increase the text size here. Sorry about that. What a list does is it holds some number of other values of any data type, including other lists. So imagine I have some group of integers that represents, let's say I have some client data, and I have a group of integers that represents ages of clients, or I have a list of ages or whatever, and I want to see what the average age of my clients are. I would have to go through that list and add up every number, every age in that list, and then divide it by the total number of elements in the list, so the length of the list, what we call the length of the list. So I could have a list of integers that would represent that information. And I've played with lists a little bit. You've seen me use them a little bit, and I've asked that you ignore them. But yeah. So let's just look at how to make a list. We can call it anything. I'm going to make a variable. I'm going to call it LST. This is what I'll often call a list if I don't have a better name for it. Don't call it LIST. LIST written like this is the type specifier for list. So there's like we've talked about, int being the type specifier and the function for the integer data type, right? LIST is for the list function that's built in. So Python, unfortunately, will just let you overwrite this with even something that's not even a list. This is legal in Python, but you need to know to avoid it so you don't override that function. Okay, so I'll call this list, LST, and I can just make an empty list like this with square brackets. I can populate it with elements. Let's just do the ages. I'll call this ages list. And I can populate this with elements 34, 58, 77, 29, 21, 31, 41, 55. Cool. So we could just imagine these as different ages, integers representing ages, and then this is just a list of numbers. So if I go ahead and print this out, whoops, let's see our output here. I'll see that again. Okay, so you can see it prints out the list of numbers. So there's a couple things to take note of here. It prints them out in the order that I put them in. It happens that it's formatted exactly the same way because I'm in the habit of formatting my lists in the Pythonic way. You could be the spaces aren't necessary, but the commas are. I could be sloppy with the spaces, although this makes for ugly code. But on the output, it's gonna put in the spaces like that. And I would suggest get in the habit of formatting your lists in the standard way or in a consistent way, and that make them easy to deal with. Okay, so you can see Python represents this as a list like this. If I wanted to retrieve certain elements out of this, so let's say I want to get this 77 here. Well, I have the ability to retrieve any given element out of this list by counting from the beginning, from the left-hand side, starting at 0, with the first element is 0, and counting from 0, so 0, 1, 2, and retrieving that element at location 2. So that location is called an index. So for every element that you see here, there is an implicitly given index that is associated with that element. So 34 is at index 0, 58 is at index 1, 77 is at index 2, right? So the way I can utilize that, the way I can access an element at a given index, I'll just say the name of my list, and I'll put square brackets behind it, and then I'll put the number of the index that I want. This is called subscripting, or sometimes a bit incorrectly called indexing. I'll use both terms interchangeably. So we could say we could index into ages list, or we could subscript into ages list. If you've ever seen, like, if you're familiar with what a subscript is in like mathematical notation, if you see like x sub 1, that's exactly what's happening here. If this were age, or x, which is somebody's age, would be a list, and then we say x sub 2 is some instance of x, right? Some given known state of x. In this case, we just think about it directly as a list, and then we say, give me the nth element or the ith element in that list. Okay, so if I print this out, I'm going to get 77. And then if I print the next one out, I'll get 29, and then the next one will be 21, and then the next one will be 31, etc., right? So 5, 6, 7. Looks like I can go up to 7. That gets me to 55. So what's going to happen if I go to 8? And before I run this, take a guess. See what your intuition tells you. If I ask for the 8th element, and I've counted up to 7 here, right? So we have 0, 1, 2, 3, 4, 5, 6, 7 indices. We have 8 elements, but we have 7. Our highest index is 7. What's going to happen if I ask for an element that's outside of that? Gosh, let me pull up my phone here. Go ahead and put your guess in Slack. Or if you know, go ahead and put that in Slack. Yeah, so we're going to get an error if we do this. It's going to say index out of bounds. And that's because, you know, this is another one of those things like, what should the behavior be? You know, should it wrap back around, right? So let's look at index 0 again. Index 0 is going to be 34. What happens if I go -1 like this? Well, I'm going to get 55. So I can use a negative number to count from the right to the left. And there's times when this is really useful. Sometimes you want to start your counting from the left bound to the right, and sometimes it's really useful to count from the end back towards the beginning. Similarly, I can, you know, just count from the right, -1, then -2, -3. It's kind of funny because if you count from the right to the left using negative numbers, you know, the rightmost bound starts at -1. So -1, -2, -3, 4, 5, 6, 7, 8. So I can ask for -8, which is kind of funny, but I can do that. That's just fine. Okay. So same thing's going to happen if I go off this end from right to left. I'm going to get an index out of bounds error, or index out of range. So if I do -9 or +8, these are both going to be index out of range. Cool. Okay, so that's the basics of a list. So I'm just showing this with integers. To be clear here, I could mix elements in here. I could say like, let's say Bill, Ted, I know. Oh God, I'm gonna do this. Wayne. These are movies from my childhood, sorry. Garth. Cool, Wayne is 77, Garth is 29. So I could do this, I could mix in elements and, you know, do whatever I need to with this list. I just want to mention this because, you know, some of you may be coming from languages where you're used to working with typed arrays or typed vectors where all the elements have to be the same type inside of a collection like this. That's not the case. We can mix and match elements to our heart's content. Generally, though, not always. Generally, though, you will have a list of all one type or all similar types, right? You might have a list of mixed integers and floats, but they're all numbers, right? So you might have a list of strings or a list of numbers or a list of other lists. So typically when you make lists, they will have a uniform type. There's a similar thing to a list called a range. Range is you can think about it as a function that generates something that is similar to a list. So range takes in 1, 2, or 3 arguments. If it takes in 1 argument, we'll just do range 10. And I'm just actually just going to cast this as a list. Range. My range equals range list of range 10. We'll print my range. Okay. What am I doing? Okay. So if you notice, this generated a list 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? If I don't cast it as a list, I'm going to get something that doesn't really look like a list. But it will, in most circumstances, function the same. I don't think I can index into a range, can I? I don't think so. Well, shoot. I stand corrected. So you can index directly into a range. But so in most circumstances, a range will behave like a list. In some, it definitely won't. But if you want to visually see it like a list representation, you have to cast it to a list with the list function. This is why you don't want to use the word list for some other variable name, because this will say int object is not callable. It sees me trying to call this variable that is an integer, and it doesn't know how to do that. Python reads this as 5, which is just nonsense. So it doesn't know how to handle that. So that's why it's important not to override your built-in functions. Cool. So range, like I said, range can take 1, 2, or 3 arguments. If it gets 1, it's gonna generate a range starting from 0 up to and not including up to, but just short of the number passed, right? So notice this range contains 10 elements, but it starts at 0 and goes to 9. It does not include 10. If I want to include the upper bound, I have to do +1. And this is a common thing to do when you want to include that upper bound. You're passing a number, usually in the form of a variable or a parameter from a function, into range to gate that range, generate a dynamic number of elements. And if you want it to be excluded, you just leave the +1 off. If you want it to be included, you'll do +1. Obviously, 10 + 1 is 11. In this case, I can just do 11. But like I said, usually this is coming from a variable somewhere. So if n equals 10 for whatever reason, and I want to generate a range of n inclusive of n, I'll do n + 1. Now I also get to tell it where I want it to start. If I tell it where I want it to start, that argument has to go before the argument that I tell it to end, right? So if it takes 1 argument, it starts at 0 and ends at the argument that I pass. If it takes 2 arguments, it starts at the first and goes to the second. So here I'm generating a range between 3 and 10 inclusive because it includes the upper bound. So notice the lower bound, the starting point, is included. I don't need to do anything to include that. If I wanted to exclude it for some reason, again, I'd have to do like +1, start just 1 above 3 here, but that's not that common to do. Okay. The third argument, if it takes 3 arguments, they will be understood as start, stop, as shown here. And the third one will be understood as the step, right? So let's say I want to go in steps of 3, and we'll just make this 100. Okay, so I'm starting at 3, and I'm going up to 100 inclusive, right? So, and I'm taking steps of 3. So notice the list generated gives me, sorry, I hope this is big enough here. 3, 6, 9, 12, 15. So it's counting in 3s, right? And maybe I could do something like, let's do steps of 9, right? So it'll go up to and get as close to the upper bound as it can, and let's do this. 102, I'm just guessing here. Okay, so 102 is, I guess, a multiple of 9 plus 3. So it'll include that 102. If I had this +1 taken off of there, it would not include that 102. I'd have to go to 103 up here. Cool. So with range, remember, one argument is from 0 to stop, 2 arguments is start to stop, 3 arguments is start, stop, step. Generally, you'll use range with 1 or 2 arguments. It's not as common to use a step. Okay, cool. That's lists and ranges. Okay, so going back to lists a little bit, I said that lists are mutable. Let's see. We talked about indexing. We'll do these first, and then we'll get to mutability. Okay, so membership. Let's take our ages list again. So this ties, what I'm going to show here ties back into the conversation about Booleans. So anytime you're writing this down, or the way I like to treat this schema is, or at least the part on types, is understanding a new type can be understood as what kind of utility is this type for? You know, what roles does it play? You know, understanding where and how to apply it is one thing, and then understanding what operations involve that type. Either use that type as an input or give that type as an output. So we talked about some operators that give Booleans as outputs, the comparison operators. So equal, not equal, less than, greater than, less than equal, greater than equal. And there's another one, which is in, and this is really an operator. It's a keyword that is overloaded, so it plays multiple roles in different circumstances. Sometimes there's special circumstances where it's not going to do this, but there are certain circumstances where it's understood as an operator. Very much like a comparison operator. We'll make its own row for this because it's a little different. And what it can do with things like lists and strings and a number of other data types, I think ranges as well, what it can do is give you a Boolean value back, true or false, as to whether something is a member of a list, right? So let's print off 33 in ages list. False. So 33 is not a member of that list. Let's see, 55. I know that one is. So that is true. So 55 is in that list. So this is a very useful thing to be able to do, to be able to test for membership quickly and easily. Okay. Okay, so list slicing. So this gets into indexing. This is like using indexing to give a portion of the list back. So one thing about list slices is they take the same sort of start, stop, step pattern, similar start, stop, step pattern to a range, and we'll look at that in a second. So let's say I want to get everything between 77 and 31 here. So 77 is at index 0, 1, 2, and then 31 is at 2, 3, 4, 5. Oops. Okay, so I'll print out the slice starting at, and to do a slice, I'm going to do square brackets again. If I just wanted to do a regular subscript for one single number, oops, I wanted to do 2, sorry, that'll give me 77. If I want to do a slice, I have to put these colons in the brackets like this. So the colons, you can think about them like separators that separate the start, stop, and step, just like that, right? So whatever number I put in to stop is it's gonna slice up to and stop at that number. So if you don't supply a value for these, there will be a value that is assumed, right? So if I don't supply a start, it will assume that you wanted to start at the beginning. If I don't supply a stop, it'll assume you wanted to stop at the end. If I don't supply a step, it'll assume you wanted steps of +1, and you can have negative steps, which will take you from right to left rather than left to right. Cool. So we wanted to slice from starting at index 2, which is 77. So that's 0, 1, 2, 3, 4, 5, up to index 5. Remember what I said, though. With range, remember how the upper bound was not included? And that's the same thing. If we want the upper bound included with a slice, we have to do +1 here as well. Of course, we all know 5 + 1 is 6. I could just write 6 here, but I'm gonna write it as +1 because I'm thinking about inclusive and exclusive, and a lot of times it's the same sort of deal. You know, you have some number which is stored in a variable, and maybe it's a number from a parameter from a function or a variable or whatever, just some number from outside, and you think about, well, do I want to include or exclude that number? If you want to include it as an upper bound, you do n + 1. And of course, it doesn't have to be called n. It could be called num or foo or whatever you want to call it. It's just a variable name. Okay, cool. Nesting lists. So, as I mentioned before, lists are collections of arbitrary objects. Arbitrary means any type. I can put any type, I can mix and match, doesn't matter. I can just store whichever objects in whatever combinations I want in the list, including other lists. This is getting into nested lists. This is not something that you need to think about deeply right now. It'll come up later. This warrants its own example, though. List O lists equals, we'll say, a list of 1, 1, 2, 2, 3, 3. Then another list, 4, 4, 5, 5, 6, 6. Okay. Another list, 7, 7, 8, 9, 9. Okay. There we go. So I have these lists of lists. They are all, the inner lists are all of the same length. They don't have to be, I mean, they can be, oops. Dang it. I keep hitting the wrong keys. Okay. They can be whatever lengths I want them to be. I can mix and match. So let's say, and actually let's just do that real quick. I'll just do this. Okay, so I have a list of 3, then a list of 2, then a list of 4. It doesn't really matter. So let's say I want to print off this 77 here. So I have to find the list that it's a member of and find that list's position in the outer list. So print list of lists. So 77 is in the third list, which is at index 0, 1, 2. So that's, let's just try that out. Oops. Okay, that gets me the list with 77 in it. And then this list, 77 is at index 1. So list of lists sub 2 sub 1 is how I'd say that. Gives me 77. And this looks a little funky with the double square brackets after the variable name, but that's how you can index into a list of lists, should that ever come up. Okay. And we're going to skip breakout. Mutability, this is what I want to get into. So this is one of our first kind of bigger concepts. All the types that we've worked with thus far do not have this ability to change their own value. You might think, well, yeah, they do. If I have x equals 10, I can always say x equals 9, or I could do x equals x minus 1, which would be the same thing, or x minus equals 1, which would be the same thing, right? So I can modify, you might think, yeah, I can modify the value of a variable. And what this is doing, this is not a mutation, this is not a change in value on the level of the data type. Like the integer is not changing, the variable is changing. So when we change the value of a variable, we're saying x equals 10, and then now the variable x equals whatever its previous value is minus 1 or something. So we're reassigning the value on the level of the identifier of the variable. We're pointing that identifier at a different value rather than pointing it at the same value and having that value change. Integers are not capable of the latter. None of the other types that we've talked about are capable of the latter. Lists are capable of changing on the data type level, on the object level. Okay, so let's look at this. This behavior is called mutability. Let's have an empty list equals like a list like this, and we'll just print off the list, and let's say I want to add something into it. I could say list equals hello. Now, I want to be clear, this is not a mutation of the list. I'm not causing a mutation. This is a reassignment. This is list equals a new value. It just happens that the new value is also a list with an object in it, with a value in it, right? So this is one way that you could add something into a list. It's a little more limited than the other way I'm going to show. Another way, if I want to mutate the list, is I can say list.append. So there are a number of tools that are built in that are only for lists. They're called methods. Every data type has some methods that are built in that are only useful for that data type. Sometimes, there will be a method of the same name that does something similar across different data types, but you think of each method as being built for that data type, right? So append is what we call a method. A method is a lot like a function. It's a whole lot like a function. It's just that it is bound to some data type like this. And the way it looks is that we'll instantiate the type, and then we'll call the method on that type, and that will perform some operation. In this case, the operation is a mutation. So if we look here, right, there is no reassignment of the variable, but the effect is the same. I didn't say list equals empty list and then list equals a different list, right? When I say lst equals something, that is an assignment of a value to an identifier. 57 is a mutation, which is different. In either case, it looks like that variable holds a list of a different value. But there is an important difference here. And I'll show this. So if we do ID, so I'm going to show another function, ID. So I'm printing off the ID of the list. It's numeric ID, so when you use the ID function, you get this numeric identity of the list. And this is just a arbitrarily assigned number that Python assigns to every variable and every object in its memory during runtime, so it can keep track of everything. So this is something Python does behind the hood, or under the hood. And we can see the IDs of everything. And this helps us determine, we can see these IDs are actually the same, right? So this tells us that the object is the same object, right? So this list and this list are literally the same list. Now, I want you to think about this like the way we think about two things being the same is a little bit fuzzy. It's a little imprecise. So with programming, we want to make that idea very precise. How are they the same? Are they the same in terms of their value? Because these two lists are not the same in terms of their value, but they are the same list, right? So think about it like this. If I take my car in for a new paint job, I get the car repainted, would you say that it's the same car? You know, if my car is black before the paint job and then I take it in to get it painted red, is it the same car when it comes out? And you know, we could get into some kind of philosophical discussion about this, but I think most of you would say, yeah, it's the same car, you just painted it. You didn't go get a different car, you just got different paint on the same car, right? So that's what's happening here, right? So the example of painting a car is like mutating the color value of the car, right? So you could think about it like my car has a my car dot color is black, and then my car dot color is red, right? So the property color of my car started out off as black, and then notice it's the same car, but I just changed the property from black to red. So same car, right? Now, here's another example. Imagine that like you and your friend have the same car. You don't share one car. It's just that you have two cars that are virtually identical. Same make, same model, same year. Maybe they have consecutive VIN numbers, which is unlikely, obviously, but you know, so they're as similar as they could possibly be. Same everything, same trim, same features. So you'd be like, oh, that's cool. We have the same car, right? But it's not the same car. It's two cars whose values, whose attributes are equal, are the same. The same in terms of being equal, right? You know, you'd say red is equal to the same color of red. You know, the leather seats are equal to the same kind of leather seats, right? Or something like that, right? So that's two cars being equal in value, but not in ID, right? And having two consecutive VIN numbers is having two different VIN numbers. So that's the idea. The first example of getting a car repainted is an example of mutation. You have an object and you change something about that object. The second example is an example of immutability or duplication, right? Where you duplicate something that has the same value or a different value, and it's a different object. So, yeah, so let's look at this. Let's look at this with a with a string as well. Because a string, we can actually do something similar. We talked about concatenation. Oh, got a couple questions here. Square brackets being associated, brackets only associated with lists in Python. Not quite. There's some aspects of dictionaries that use square brackets. There's some, but we'll get into that as well. We can also index. So what we just covered with indexing and slicing into lists, we can index and slice into strings as well. So let's look at strings. I'll call this string equals hello. So if I do, remember we can concatenate strings. If I do string equals string plus space plus world, right? Let's do something similar with this. This is going to seem fairly similar. Well, we'll start it empty, and then we'll do hello world. Yeah. We'll do hello, and then we'll do string plus equals world. We'll keep it consistent. There we go. Okay. All right, so remember how I said strings are immutable types. Strings, all the other types we've talked about up until lists are immutable. So if we look at this list, I start with an empty list, I print off its ID and its value, so obviously we see the ID and then an empty list, and then I append, this is not a reassignment to the identifier, this is a mutation of the object itself. I append hello onto it, and then print off its ID and its value. So we can notice that even though the value changed, the object is considered the same object in memory. And it literally is. In Python, there's a group of probably contiguous bytes in your memory that represent that list, and it's the same bytes, or at least it starts in the same place in both of those cases. So let's look at something similar with the string. We print off the ID and the value. Since it's an empty string, it's showing us the contents, but since there are no contents, it just doesn't show us anything. Then we print off, we concatenate hello and concatenate world onto it. We could just do hello, just for the sake of simplicity. What's wrong with my... Okay, there we go. Had to restart my server there. So notice the ID changed here, right? So the result of a concatenation with a string gives back a different object. That is the concatenated version, but it's literally a different object. So this is an immutable operation because I'm reassigning a different value that just happens to be related to the prior value, but it is considered literally a different object. So I know it might seem like I'm kind of picking a nit and being like overly precise with this, but it's a concept that's really worth establishing well, because there are implications of it. And this, I'm not necessarily getting into all the implications yet, but once you start facing some of those implications, understanding mutability will be paramount for dealing with it. Okay. So because lists are mutable, sometimes you'll want to let's do this. List 1 equals, we'll say A, B, C. And let's say I want to append D to this. I want to get a version of this list, excuse me, with D appended to it, but I don't necessarily want to alter list 1, right? So you might think, oh, well, I'll just copy list 1 and then I'll alter the copy. List 2 equals list 1. So we could say list 2, and I'm going to be transparent here. I'm doing this the wrong way to show you why not to do it this way. So, and then you might go, okay, so let's just print list 2. Verify that worked. Okay, great. List 2 seems to contain the data that I wanted, right? So this example, and I've seen a lot of, I give this example because I've seen examples, I've seen this kind of thing a lot. So in terms of being scientific about testing my assumptions, what have I not tested here? What can I do to verify that what I did has worked or not, that I didn't do? Oh, I'm sorry, there's a question here. When time permits, oh, why is index not accurate? I suspect what you mean is why is it not one-based? Because zero-based indexing was established as a norm in programming languages in like the, well, geez, actually maybe the 50s. It's been around forever. There are also like norms around this in higher math where you think of, yeah, you just, I guess the easy answer is that it's a convention that goes back like many decades, if that helps. Okay, so we've got a comment here. Make sure, oh, you weren't interrupting. I was just giving people time to answer the prior question too. So the comment is, make sure you haven't changed list 1 by list 2. Yes. Okay. So in order to do that, we would have to print out list 1 as well. Right. So this might appear that this line right here, 76, might appear like a copy. This is, sometimes it's called a shallow copy. That's the term for this. I don't even like to call it a copy because it's not, it shouldn't be regarded as any kind of copy at all. What this is it's an assignment of another identifier to the same object, right? So what we literally have here, and we could prove this by printing off the ID, what we literally have here is one object that has 2 identifiers pointed at it. And we can see that because the IDs are the same. So this is list 2 and list 1 have the same ID. They're the same object. So if you do want to copy, which there's a lot of times where you do, you want to use the copy method. So you'll say dot copy, and you need parentheses after it. There are no arguments to the copy method, but you do need the parentheses. If you don't put the parentheses, it's not gonna actually invoke the copying. It does something else. Not what you want. So now we look at the IDs and they're different. So now let's see, are these going to be different values? Yeah. So now we've modified list 2 and not list 1. So this is called a deep copy. Or more accurately, it is a copy. It actually makes a copy of it. So this gives me a list of the same values in a different ID, so I can manipulate that without altering the original. Cool. let's have a short break. Let's reconvene at 5 after the hour. Okay, so new concept, loops. Now this relates strongly with lists. Loops and lists really go together. So back to our overview, we just talked about lists. Let's do a little bit of abstraction. Variables are abstraction. Functions are abstractions. Functions have two phases, which are definition and invocation. Control flow is the bit about if, elif, and else. Relates to booleans, because booleans are the essentially conditions that let us use if, elif, and else dynamically. And right now we're going to get into iteration. We're going to talk about for loops. So as of once we get in through this part of the lesson, we will have a complete, simplistic, but we'll have at least one tool from every category. We'll have something from every category here, which means you basically have a complete set of problem-solving tools now. Okay. Huh. Okay. Sorry. I'll have to take that question after class, I think. Apologies. Cool. So loops. So let's just quickly look at the syntax of a for loop. So we're going to use the for keyword, for, and then we get to name some identifier. I'm going to say L for element, or LE for element, and then in. Now this is what I was talking about in being sometimes being kind of treated as a special keyword and sometimes being a Boolean operator. In this case, it's the keyword version. So for L in, then some collection of elements, right? Which could be a list. So let's do our ages list. Why don't we do this? Let's use this for loop to calculate the average age of the people whose ages are represented in this list. Okay, so for element in the ages list, let's just start off by printing off the element. So notice again, so we have for and then our own custom identifier name. Again, this is an identifier name, just like saying LE equals some value, whatever. It's a lot like a variable, but you can think about it like in a for loop, this is like a variable that gets reassigned in order to every element in this list individually. So, the first time this loop runs, LE is gonna be 34, then LE will be 58, then 77, then 29, etc. So let's just run this. So you can see it prints off vertically like that, and that tells me that this print is running multiple times and kind of marching down the line there. Sorry, I see this conversation happening here. Apologies for the confusion around NodeMon. That generally takes some setup. I don't want you all to get worried about the way, don't worry about necessarily setting up your code exactly like mine is. My environment is actually the result of a lot of setup. So as a plug-and-play solution, really I recommend if your computer will run VS Code to use VS Code, it's much more of an industry standard. There are some other additional problems that you might have to work around. Atom is a great backup editor. If you're executing your code for now, you can do Python, or depending on your system, you might have to do Python 3, and then your file name, src Python main. So something like that, and then you'll just have to run that command in your terminal every time. It takes a couple extra clicking steps, but setting up NodeMon is kind of a whole can of worms. So I just wanted to get on that before people think that I'm expecting everybody to set up NodeMon. So apologies. Okay, anyways, back to for loops here. Okay, so for element in ages list, and let's call this age. Actually, that's a better name for this, because that's what it is. It's an age, a single age, one at a time. Okay. So this is a lot like saying age equals ages list sub 0, and then sub 1, and then sub 2, sub 3, etc. Right? But rather than having to write it out every time, a for loop just does that automatically for us. And then everything that's indented in the for loop, we're going to work with age, right? So maybe I could do something like if age is less than, I don't know, let's say 40, print you're still a whipper snapper, or something like that. And we'll do age. So 34, 29, 21, 31, you're still a whippersnapper. Okay. So you can see we can use, indented in this for loop, we can use age as if it were a variable, and we can just use it and it'll get reassigned every single time, and we can do this, whatever this whole process in the for loop is, we can perform that process on every element in the loop. The for loop will automatically terminate once all the elements in this list have been exhausted. So as soon as we get to 55, the for loop is smart enough to stop running loops. So we don't have to tell it how or when to stop. So this is called traversing a list. So like I said, let's use this to calculate the average age. So if you don't know, the way you calculate an average, you have a list or some number of recorded events, numeric events, which we have here. So we have a list of data points. We take the sum of those data points over the number of those data points. So in this case, we determined, I think there were 8. 1, 2, 3, 4, 5, 6, 7, 8. Yep. So we would sum all of these numbers and then divide that sum by 8. And that'll give us the average. So let's do this. Let's say number elements we'll say number of elements well, let's call this count. Let's call this elements count equals, we'll start this at 0. That'll be our num, and then elem's sum. Let's call this the sum of elements. So for elements count, this will be pretty easy. Every time we go through an element in the list, we're just going to add 1. We're just going to plus equals 1, and then every time we go through a new element in the list, we will plus equal the element value, which is age. I change that to age. Let's do this. Ages. So ages count and ages sum. So with ages count, we just add 1, and with ages sum, we add the age successively. So after that for loop is finished executing, I can do sum over num. So that's, oops, I need to change that. Ages sum over ages, oops, count. So 43 and a quarter is the average age in this collection. Excuse me. Something in my eye. Apologies. Okay. Hopefully it'll stop bothering me soon. Okay. Is this landing all right for people? Or people, if you're confused, feel free to put in any questions you have. I'm assuming that this is landing all right for people since I'm not seeing any questions. BD I take as thumbs up. Cool. So this pattern here is an example of the accumulator pattern. And this is, so sometimes the accumulator pattern is, it's a bit reductively called the everything algorithm, although there's it's earned that title fairly well, because there are just a ton of problems whose solutions look like this. An accumulator pattern is not necessarily the best solution for a given problem. Sometimes there are often better ways to solve a problem than accumulation. The cool thing about it, though, is it is often, so often will just provide a working solution. So if you just, and a lot of times that's what's important. I think one thing that's easy to overestimate in when you're just starting programming is like performance. Performance is important. I like writing performant code. Everybody likes their code to run fast and run well and everything. A lot of times it just doesn't matter, though. A lot of times performance isn't as big a concern. A lot of times performance comes at some cost, like potentially maintainability. Maintainability is easy to underestimate until you've been programming for a while, and then you write some things that are really hard to maintain and come back and look at, and you start valuing maintainability a lot more. So accumulator stuff is so generic and so easy to read after you've been programming for a while. It's just a pattern that you've seen thousands of times. So it's an easy place to start solving a problem. And a lot of times you'll write an accumulator solution and you'll look at it and you'll be like, oh, there's an easier way to do this, or there's a better way to do this. And it becomes clear once you've done the accumulator way. So even it might feel like a brute force way of solving things, and a lot of times it is, but don't let that stop you when you're just trying to put together a working solution. A clunky working solution is nothing to be ashamed of. If it does what it's supposed to do, like, you won, so congratulations. That's what's important. If it needs to be optimized, that'll often be clear after you've got it working. So it's easy to optimize something once you've proved that you can make it work. Sometimes that means diverging pretty severely from your original approach, but often that divergence becomes clear once you've just taken a simple sort of brute force approach. Then then it's easy to do the other one. Cool. We got a question here about, can you use len? Yes, we could use len. There is an easier way to do this. There are two functions that are built, and I was going to show that. But I wanted to show, I just needed an excuse to show for loops. And this is a good, simple problem that has just a bit of everything. So somebody's bringing this up. Could we take the mean age like this? We could do sum of ages list. So there's a function that takes in a list of numbers and returns the sum, and put it over the len of ages list. And len will automatically calculate ages count, and sum will automatically calculate ages sum. So this is actually a good example of what I'm talking about, right? There are built-in tools in Python that'll just do this for me. This is a better solution. It's easier. It's less code. It's actually more maintainable, easier to read, and better. But let's say you don't know that sum and len exist. You don't need to. You can write code now to determine both of these things. So, I mean, you should know that sum and len exist. You should know these functions. There are a lot of built-in functions and methods in Python. Some of them are like, you'll use them all the time, and some of them you'll use very seldom. There are methods and functions in Python that I've never used, that I'm aware of, that I've still never had a practical reason to need. And that's not to say that I won't. Maybe at some point I get into a project where I use those all the time, but to this point I haven't. So the cool thing is, and this is what I'm talking about the accumulator pattern. A lot of times, like especially as you're learning, get good at the accumulator pattern. Get good at understanding the nuances of the accumulator pattern, not only because it's central to programming anyways, but because it will fill in the gaps of all the things that you don't know yet, right? So that's a great question. Can you use len? And the question was just about len, but yeah, you could absolutely use len. If you knew len but you didn't know sum, you could do len for one of them and then make the problem work by doing sum manually with an accumulator pattern. So much can be done with the accumulator pattern. I'm like listening to myself say accumulator pattern and thinking like, you all are probably annoyed at how much I'm harping on this. To me, I feel like I'm underselling the value of it. So like I can't overstate its importance. It may look simple, but it is very much central to so much of programming. So just in short, accumulator pattern is going to be, this is actually two accumulators. We have two accumulator variables. So the accumulator pattern is we start some variable, we run through some loop, we initialize a variable, we run through a loop, and then we modify the variable in the loop according to whatever the logic in the loop is. Generally, you're going to start the variable at with either, if it's a number, like a zero-ish value, or 0 or 1 or something close to 0. So, I think about it like as a neutral value. If it's a list, because you can have list accumulators, or a string, you might start at empty string or empty list. So there are accumulation patterns that are like that. So generally, you'll start off with something that's zero-ish or neutral or empty, something that you can think of as neutral, and that's kind of a squishy term. It's an imprecise term, but something that you might think of as empty or neutral. And from there, you can add into it. So I would call that an additive accumulation pattern. There are other cases where you'll initialize your accumulator with some small amount of elements in it, maybe just to get you started, or maybe you're accumulating onto something that already has a large number of elements. Both of those are less common, but still within the realm of what I would call an accumulator pattern. I use the term accumulator pattern to mean a very wide variety of things. Sometimes you'll hear something called a decrementation pattern, which would be like if I had started this at like, maybe if I start a number at like 10 and then decrement that number under certain circumstances and then find out what it was reduced to. I think about that as an accumulator pattern. Broadly speaking, you have a variable, you have a loop, you modify the variable in the loop. That to me is not really a different pattern. Whether I'm adding to it or subtracting to it is trivia, and that that's trivia according to whatever problem that I'm trying to solve. So sometimes you'll hear the term. Excuse me. Sometimes you'll hear the term decrementation pattern, but I'm just gonna call all of it accumulation, even though that might technically be a little bit wrong at times. When you write 4 ages in list, will Python always allow you to use the word after 4 as a variable? Are there words that you cannot put in there? Yeah, so this gets back into good variable naming, basically. The question is, as I understand it, correct me if I'm wrong, but throw a pass in here. Will Python always let you use whatever you put after 4 as an identifier for the data or a variable name? Syntactically, that is what that part is designed for. Python will attempt to understand that as a variable name. There are times like I said, this gets back. This is part of the conversation about like good variable naming. I could call this len. I just showed you a function named len, right? So let's say I'm trying to do the same thing for whatever reason, and I just decide I'm just going to call for len in ages list. That's not a great. I don't know why I would use that name, but let's just say I decide to do that. Well, now I just overwrote my len function. So if I do, let's take out count, right? This is going to give me an error. Type error, int object is not callable, right? So I overwrote my len function. So yes, it allowed me to do that. If we look at this, if I just printed out, if I just printed out ages sum, it absolutely let me do that. I mentioned this before. I wish it would stop you from doing this. I wish it would tell you, no, you can't overwrite a built-in function. You're not allowed to do that. Unfortunately, you're absolutely allowed to do that. I could call this print, and then my print function would be gone. I could do it, but I don't want to. So with functions, built-in functions, you need to remember which ones. You remember the built-in function names that you use a lot and avoid those. We get another int object not callable, right? Because I'm trying to use print. So you got to be a little careful. It's just best practice, obviously, not to overwrite built-in functions. There are certain words, like if I tried to use for, this is going to cause a different set of problems. This is invalid syntax. So for, so this looks valid in here, but for is a keyword, not a built-in function. So it's weird. Python will allow you to overwrite built-in function names, but it freaks out if you try to use a keyword. So for is a keyword, in is a keyword. Same thing, invalid syntax. def. Remember we talked about defining functions. Same thing, that's invalid syntax. Return, again, for functions. So there are certain words it'll like yell at you if you try to use it, and certain words that'll be like, okay, you can use that, but you have to just remember not to use it. So it's a good question. So to summarize the answer to that, it will always attempt to understand this as a variable name, even sometimes when maybe it shouldn't. So cool. Let me know if that's helpful. Okay. So this is just a generic description of for loop syntax. Again, just for element being some name, some identifier name that you get to choose within bounds. Then the keyword in, we got to have that in there. So for element in list doesn't have to be of the list data type. In fact, and this is why we showed range, quite often we will iterate through a range. So this is kind of specific. I would rewrite this as for so for identifier. Apologies if that's misspelled. I am unironically dyslexic, so that looks right to me. I'm just going to roll with it. So for identifier in, you call this collection or iterable. Some iterable body of code. So that's your for loop syntax, kind of in a generic sense. Traversing a list, we'll talk about list traversal. This is traversing a list. So we would say we're traversing the ages list. So for age in ages list is traversing, walking through that list. Let's see. So again, accumulator pattern, initialize the accumulator variable. Usually it's some neutral-ish, empty-ish, zero-ish value. Repeat some process modifying the variable or the object. Remember we talked about, we can reassign a variable, or we can mutate an object for the objects that can be mutated, right? So lists can be mutated. So that's another way of doing an accumulator. 6 of one, half a dozen of the other. We cause some modification either on the variable level or on the object level. And then when the loop terminates, you should have the correct value, or at least a value you can turn into the correct value in another set of steps, possibly another accumulator. Some accumulators using an integer. So this is what we just looked at when we're doing where we're accumulating onto this numeric value. So we tend to think about accumulator patterns as being linked to the type that they're accumulating on. The thing that's being accumulated on, I'll often call the target. In that first example I gave, we had multiple targets. You can absolutely have multiple targets. So the target is the thing that you're altering for accumulation. That's your accumulator, right? So we'll tend to talk about accumulators as like integer accumulators or float accumulators, or we can think about those as just numeric accumulators. So numeric accumulators, or counter, if you're counting something like I was doing in that first example, I was counting the number of elements, which is what len does. So if you're counting something, there's different ways to count things, or reasons to count different things. Maybe I only wanted to count ages over 35 or something. So that's a kind of numeric accumulation. But we can also have list accumulators. We can have string accumulators. So we think about every type as having sort of an accumulation pattern linked to it. I guess every type except for none, because it only has one state. So like we can initialize it, but we can't change it. So we don't. I don't think we would talk about like having a none accumulator. Um, Although there are times where I've started my accumulator as none because maybe I don't know. I'm gonna find out by iterating whether I need it to be a number or a list or a string or something. Maybe I don't know its type right away. And then I would go into a list style or a numeric style or whatever style of accumulation that I need. So yeah, just important to remember that. So let's just look at a let's look at a list accumulator. I'm just going to call this list. We'll stop thinking about this as ages. And I'll say for LE in list. Quick side note, like you'll often see me just give things really generic names. That might seem confusing. It might seem like, oh, well, Clark always calls that LE when it's an element in a list or EL. I will often use just simple 3 or 4 letter variable names. You can take note of those, make your own variations of them. I just do it because I'm lazy, and once you learn to program, the hardest thing left over is variable naming. So I just recycle variable names because I don't want to think about it. So yeah, we'll just say for LE in list. Let's do. So this is our source, right? This is the source or our iterable that we're iterating through, that we're traversing. And let's call this ACC for accumulator. And ACC dot append. And let's rename this. We'll say squares list. So this will hold squares of all the numbers in our list. So we'll append LE squared. Oops. And then print squares list. Okay, cool. So here's all our numbers squared. So this is an example of a list accumulator. And it's pretty straightforward. We just start an empty list and accumulate into it. Obviously, we could have more lines of code in here. We could have ifs and elses and make things complicated and do whatever we want. But if we just want to collect squares, we can just do it that way. Nice and easy. So Booleans, this is kind of a weird one. The Boolean accumulator has its own special name, which is Boolean flags. So everything else, every other type, we call it an accumulator, or maybe a counter or whatever. With a Boolean, we'll tend to call it a flag. And the thinking behind that is, you use it to flag some process, right? So maybe I could do like print, or let's see, for num in list. Let's have our Boolean flag. What should we test for in this list? Let's do this. Let's have a numeric accumulator, and we'll see if the sum of everything is sum greater than 100 equals false. This will be our Boolean flag. So we'll have 2 accumulators for this. And I'll just say tally plus equals num. And then I'll say if tally greater than 100, then I'll flip my flag to true. And then afterwards I can say if sum greater than 100, print oh gosh, that's got to be a string. There we go. The sum was greater than 100. So notice, remember, the definition for a condition in an if is any expression that gives me true or false. Well, sum greater than 100 is a Boolean flag that holds a value of true or false, so I can use it as a condition, right? So I can, I'll set it in my loop, and then we'll print off. We'll use it as a condition in this if, and then print that off. Maybe if the sum is greater than 100, I want to stop looping, and this will get into something else we're going to talk about here soon. I can stop the loop by using the break keyword. Now, break bears only on loops. And I want to make something clear. There's somewhat of an aesthetic similarity between a loop and an if. I'll hear people talk about if loops. A loop repeats a process. An if just checks a condition and runs the code if the condition is true. So they're fundamentally different. So we don't talk about we don't think about ifs as being loops. And yeah, so for is the looping construct that we've looked at, and then if is a conditional construct. So when I say break bears on loops, I don't mean it bears on the if. It has nothing to do with the if. It bears on whatever loop it is most immediately within inside of, which in this case is this loop here on 147. So break means it's going to stop the loop. Let's just print off the tally to see how high we got there. 169. So we got up to 169, and then we broke the loop. Yeah, cool. Okay, so that's Boolean flags. Is prime. The is prime function. So this is an example of writing a prime number detecting function that uses a Boolean flag. To be clear, this is maybe my least favorite way of writing this particular function, of writing an is prime function, but you can do it this way. And it's actually a good example of Boolean flags. It's just not a great example of an is prime function. And I'll show you why here. So let's do this. First, I'll stub out my function, and we'll write a test. Oops. Keep doing that. So I want to see if 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So I'm going to see true or false. I want this function to return true or false as to whether each of these inputs are prime numbers or not, right? So I'll go through this prime algorithm. So we're going to start a Boolean flag called prime. It'll be equal to true. If you think about the algorithm, a working algorithm for determining whether a number is prime, a number is prime if it has no other divisors other than itself and 1. So if we check every number between starting at 2 up to itself, but not including itself, we can determine if that number is prime if we found any other factors. So let's just write a loop to do that. So we'll say for I in range. I haven't talked about range. I meant to, but we can loop through a range. Often I is used as sort of a generic identifier for an element in a for loop. There's a long history of this. This goes back to like this is a convention, I think, from Fortran or before. So this goes back to at least to the 50s. And there's not like, it doesn't do anything special. It's just a convention. So if you're wondering why am I using I, that might seem really random. It's a standing convention, and as you program more, you'll learn to associate I with an element from a range, usually a number, or an element from a list, just some element that you're looping through, right? So we'll say for I in range, and we want to start at 2, and we want to go up to n, and not include n, so we won't do n plus 1. So now, what happens if my number is less than or equal to 2? I'll have to say if num is less than or equal to, well, if it's less than 2, excuse me, if it's less than 2, I'm going to set prime equal to false. We're just not going to consider numbers less than 2 to be prime. And then if I in range, or excuse me, for I in range 2 to n, we're not going to, like I said, the upper bound is not included, so we're not going to check n here. The n itself, or what I'm saying is I will never actually be equal to n itself. We can say if n over I has a remainder of 0. So the way I get the remainder, remember, and this is why modulo is so important, is because often you want to know what factors things are, right? If something is a factor of something else. So this tests if I is a factor of n. We can say prime equals false. Is there an easy way, somebody's asking, is there an easy way to expand a built-in function or see underlying code, or would that underlying code be in C or some other code like from assembler? That's a really interesting question. If you want to stay on, I would love to take that after class. The answer is a little complicated. But yeah, that's a super interesting question. All right, let's see here. So for I in range 2 to n, if n mod I equals 0, so this tells me if I is a factor of n, then we know that it's not a prime number. And then after it's all said and done, we'll say return false. Oh, excuse me, not return false, return prime. Excuse me. Okay, so let's see. Oh, I called that num. I want to call that n. Oh, wait, what? I'm all over the place with this. Okay, good. Cool. So, let's just do this. See if I can get away with this. Is it gonna help me? No. Ah, alas. Anyways, so 0 and 1 are not prime. 2 and 3 are prime. 4 is not. 5 is. 6 is not. 7 is. And 8 is not, right? So this is kind of a long, annoying way to test this function. Usually the way I like to test this is in a loop. We'll say for I in range. We'll just start at 0 and we'll go up to, let's just say, 20. which will actually be 19, but I don't really care. The upper bound isn't that important. Oh, come on. And then I can print off I, and then pass I in here, and that'll test every number between 0 and 20. And then I can see the number next to the result. So this will work. There are ways to optimize this. We can, if you think about how factors come, they tend to come in pairs. So we don't actually need to check any number above half. So we could check I over 2. If we do that, we need to cast this as an int because we can't have a floating point number in a range, since range gives essentially a collection of integers. You can't set a boundary with a floating point number. It's too ambiguous. Python will yell at you if you try to do that. So I'll cast this as an int and do int over 2 like this. So that's one way to optimize this, but you can actually optimize this even further. The smallest set of numbers that you need to check is actually the square root. So in order to take the square root, we can do n to the power of 1/2, where this lower term here is the nth root, whatever, so the fifth root, whatever. So if you want to do the square root, you can just raise something to the power of 1/2 or 0.5. Either way, I always like to just lay it out this way, just my own personal preference. But so that's the smallest set of numbers that we could check, and we can also include it. We also need to include it if we do if we do half or excuse me, if we do square root, we need to include it. Yeah. All right. So that's a slight optimization. I do prefer to write this function differently, and I find that this kind of tends to be true with Boolean flags in general. In general, I don't end up using Boolean flags that much. There's some times where they come in handy. Often I'm writing fairly small functions, so I'm just using return instead. So what I like to do is just get rid of that flag and return true. So this is, there are other optimizations that you could do to this, but this is sort of my vanilla quick go-to for an isPrime function. Loops as filters. So we kind of looked at this. This is just exploring sort of an example concept where I did the, if the age was less than 40, I printed off you're still a whippersnapper, right? So we could have accumulated all the whippersnappers into a whippersnapper list. Oh, that sounds fun. Let's just do that. And that would be filtering out all the whippersnappers, so you knew who wasn't a whippersnapper and whatnot. Okay. Of course, I seem to have deleted that code. Let's just do this. So we could say if age less than 40, we'll call this snapper list, equals this, then we will and then we could print off snapper list right there. Oh, I forgot the colon. Okay, so these are all the people under 40. So here I'm just filtering out all the ages under some arbitrary bound. We talked about break. Gosh, shoot, I meant to show this in the... So one of the advantages of the writing is prime with returns instead of a Boolean flag is, imagine I have a number like 10 or 100. If let's do this in the less optimized way. So I don't want to check right away. I'm going to check 2. 2 is a divisor of 100. 100 over 2 is 50. We know that has no remainder. We know 100 is not a prime number. So with this setup, it's going to check 100 over 2 equals 0. This is true. It's going to set prime to false. And then it's going to just keep checking numbers. And we don't need to do that because we already determined that this is not prime number. It's going to keep checking all the way up to 99. So as soon as we find a prime number, we can break. And that'll stop the loop. So break is it's a really good tool to have in your tool belt. You don't use it that much, but when you need it, boy, does it come in handy. And it can be used for optimizing things like this, or sometimes it's more or less logically necessary, depending on how you're solving a problem. Like I said, though, the reason I prefer to return is because I mentioned this fairly quickly when we first started talking about functions, but return, once your function encounters a return, even if it's in the middle of a loop, it stops executing any further code. It does not go on and check the next thing. It outputs the value, and that outputting of the value means that code execution for this function is over. It's completely done. So this is a de facto break. It's even more breaky than a break because it'll break this loop, and if this loop was in any other loops within the function, it would break that as well. Not because it's trying to break the loops, but because that is the nature of returning a value from a function, is that it stops further code execution in that function. So that's another reason I prefer to do it that way. I'm not going to have time to get into continue, I don't think. Pass. Okay, cool. We're close enough to the end. The only major concept relating to loops that we didn't cover is continue. I say major concept. It's not huge. It's related to break. So break stops a loop. Continue skips one iteration. So it just says, oh, just skip this iteration and go to the next one. So it stops code execution within that for that iteration and then moves on to the next iteration of the loop. So there are times when that can be very useful as well. But yeah, so that's I'll leave it to you to kind of explore continue as a concept. Feel free to chat about it in Slack. Feel free to ask me since we didn't get to it. We weren't able to get to the stuff on list methods. You can kind of explore these, although I will be going into I'll be going through this list at some point fairly soon, and we did explore what I would consider the important concepts. So just quick before we wrap up, quick takeaways for lists. We'll just do some kind of bullet points here. Lists are mutable, meaning their value can change without changing the ID. So we can change the value and it's still the same object. We have that capacity. There are some other in here. There's some other mutable methods that change the value in different ways. And like I said, we'll be looking at those. So that's one aspect of lists. They're a collection of arbitrary elements. Including other lists. They can contain other lists. There's no boundary on how small or big they can be. They can have a size from 0 to up to whatever. You can iterate through them with a for loop. And every element has an automatically assigned index. So this is probably one of the most central things to understand for lists. This is also true for strings, for the characters in a string. Each character lives at a specific index. So what that means is, for however many elements there are, each number or each element is numbered starting with the first element at 0. Always with the first element at 0. So you have to get used to zero-based counting. It's something that I still make mistakes with, but it's a little bit of a guess and check sort of system, and you'll get there eventually. So yeah, remembering about indexing, and we can pull slicing out of that as well. So these are the quick notes that we covered for lists. Okay, cool. Sorry about going over time there. The timing for today was kind of funky. I apologize about that, but yeah, we'll be getting things going on time in future lectures. If you want to go and get on with the rest of your day, have a good rest of your day. I release you out into the world, and if you want to stay on for questions, we have some standing questions in Slack. I know we have at least one about looking at the code. Yep, you're welcome. I'll see you on Monday. You have a good one. Have a good weekend, everybody. Everybody's getting out of here. Have a good one. Have a great weekend. Yeah, thanks for sticking around on your Saturday. And then, let's see. Let me just stop the recording and we can get questions going.